I would now like to discuss reactions with heavy ions, which can potentially lead to the formation of new heavy or even super heavy nuclei. One of the most popular reactions is the complete fusion reaction. When a bombarding nucleus irradiates a target, it has enough energy to overcome the Coulomb barrier, bringing these two nuclei into contact, as a result of which, probably, a heavy nucleus swallows a smaller one, or better to say that a small nucleus is amalgamated by a heavy one, and you will get a new formation which will have a mass equal to the sum of the masses of the interacting nuclei. Since all the energy is extinguished in the target, this new nucleus formation will move towards the beam, and its recoil energy can accurately be calculated. For this, of course, it is desirable to have head-on collisions, the aiming parameter being 0. But even if the aiming parameter is not 0, amalgamation will still occur and they will merge anyway. Only this nucleus will rotate due to the fact that a large angular momentum is introduced. But according to the same laws, its recoil energy will be the same as it should be with the complete elimination of the kinetic energy of the nucleus in the internal degrees of freedom of the target nucleus. Other reactions behave differently. If we did not have a complete fusion, but only a partial one, then one part would fly off in one direction and the other in another direction. All these kinematics can be calculated depending on the masses of these parts and the angles of their flight. These reactions are called incomplete fusions, even in head-on collisions. And in the case of a tangential collision, of course, all the kinematics will change depending on the momentum that the products of these reactions are introduced. Let us return to the compound nucleus. This is very interesting. This means that in the compound nucleus, Bohr, who proposed a description of these reactions, split it, so to speak, into two parts. He said that the first part, or the first stage, is when the particle hits the target, is captured in the target, and all happens very quickly. For a light particle, it is only 10 to the power of minus 21 seconds. For a heavy one, I can add, of course, a little more, around 10 to the power of 19 seconds. As a result of this, fusion is formed, and a new nucleus is formed. This new nucleus has a very small excitation energy divided by the number of nucleons in it. It is significantly less than the binding energy of neutrons in this nucleus. This nucleus must wait for a very long time for a neutron to be ejected. It leaves the nucleus when energy is concentrated on it. This is the only way to cool this nucleus. Therefore, it waits until the energy fluctuates on one neutron, which will then be ejected. This will take about 10 to the power of minus 19, even 10 to the power of minus 16 seconds. During this time, the nucleus completely forgets the way in which it was formed. There is a nucleus, it is heated, and it starts to emit a neutron, then gamma rays, and then it cools. See what it looks like over time. This is the energy of excitement with a large range. The collision time is approximately 5 times 10 to the power of minus 23 or 10 to the power of minus 22 seconds. And the neutron emission time is 1, 2, 3, 4 orders of magnitude longer. At the same time, thermalization of the nucleus occurs rather quickly, and the spectrum of evaporated neutrons will be described by the Boltzmann distribution. It is shown here, a typical distribution corresponding to temperatures of 1, 2, or 3 mega-electron volt. This temperature can be calculated to be, for example, 1.25 mega-electron volt, with an excitation energy of 40 mega-electron volt for a heavy nucleus. And now we will look at the probability of neutron evaporation according to the statistical theory of the nucleus. The nucleus, which has a ground state, reaches higher energy levels during excitation. These discrete levels become continuous when the width of the level becomes wider than the distance between the levels. And then this density level grows according to e to the power of ex. If we want to look at the neutron emission on the nucleus, which is located here, we have to write the ratio of the density of levels of the initial state and the density of levels of the final state. The likelihood will be shown here. Here, G sub n will be the density of levels of the initial state minus the density of levels of the final state, and this will be the probability of emission of this neutron. But this nucleus can simply divide at this point. The division barrier is responsible for division, and then we go down one floor after emitting neutrons in competition with fission. Either we will lose this nucleus in fission, or if we do not lose it, it will descend to an energy level approximately equal to the binding energy of neutrons. And then we come to the energy of the nucleus instead of the initial energy of 40 megaelectron-volt. We come to an energy of 31.5 megaelectron-volt because we have to subtract from this energy the binding energy of the nucleus and the kinetic energy of neutrons. But this is not yet the cooling stage. This is a rather small portion of the energy taken from the nucleus, made from 40 to 30 megaelectron-volt. The situation must repeat itself one more time. It repeats once, then twice, then 3 times, until the energy of the compound nucleus is lower than the binding energy of the neutrons. That is, the cooling of such a hot nucleus should proceed by cascade evaporation of neutrons, but each time the fission will complete with the neutron emission. Here is how it is shown. And then the cross-section for the formation of a nucleus in the ground state will be the cross-section for the initial state in the excited state, multiplied by this ratio of the probability G sub n to G sub f to the power of x, where x is the number of steps, or the number of emitted neutrons. This value is approximately 0.01 to the power of 4, which will be 8 orders of magnitude. That is, during this cooling, a great number of the newly formed nuclei is lost. We can reach the main state that we want to get to, and which we want to investigate, only with a probability of 100 million to 1. It turns out that the excitement process is rather problematic. And now we will see how this nucleus should be obtained so that this excitation is small in order to reduce the number of neutrons. Then we will try to obtain it via a different method. We will take a light particle, a heavy target, then a slightly heavier particle, a slightly lighter target, and a slightly heavier particle and an even lighter target. That is, we will change the mass asymmetry between the projectile and the target. This is what it looks like. This is the excitation energy. This is where I get the same nucleus all the time. Here I increase the mass of the projectile, and the excitation energy grows. Why is that? Because the Coulomb energy is increasing. If I take carbon instead of helium, and then take oxygen as a bombarding particle, then the Coulomb barrier increases. And the process requires more and more energy for the nuclei to converge and to merge. But this will inevitably affect the excitation energy of the compound nucleus. This is more or less a typical pattern where carbon irradiates uranium. Here is the excitation energy, and we see that 3 neutrons are emitted here. Here 4, here 5, here 6, here 7, and here 8. But all this is an exponential decrease in the cross-section as the number of neutrons increases. There is a very unfortunate summary. We need to have a decent projectile to get to the big atomic numbers. By increasing the projectile, going from carbon to oxygen, neon, magnesium, and then even to sulfur, we naturally increase the Coulomb barrier. By increasing the excitation energy, we increase the cooling losses due to neutron emission, and the resulting nucleus in the ground state is obtained with less and less probability. For example, we reached element 110, which was done at FLNR. We took plutonium-244 and sulfur-34. This section was half a picobarn, and look how sharply it decreases. This was already at the very limit of the sensitivity of the experiment. Why is that? By the way, the calculation that predicted superheavy elements, where the fusion barrier is high, shows that we have not yet reached this region. Furthermore, we are moving through a narrow section where the fission barriers are small, where the probability of fission is high, and therefore at each stage of neutron emission, the losses become bigger and bigger. So this one, what we call hot fusion, is shown to be the next stage after neutrons. This is how we got to the element 110. Here is the half picobarn section, and you can see that there is a long way to go to get closer to what the theory predicts. Considering fusion reactions, this is a theoretical prediction. Lead is a doubly magic nucleus, a stable nucleus, super heavy, high stability is expected for it, with the number of neutrons totaling 180 and the number of protons being 114. It took 15 years for the process of neutron capturing to reach this section. And another 20 years for heavy shells, or the so-called hot fusion, to reach this section. At this time, we haven't yet reached this place.